Okay, so hello everyone. I am Kailas Prasad, PhD scholar from Nano Electronic Device and Circuit Lab, Department of Electrical Engineering, IIT Gandhinagar. So this is our live session 10, and uh, the goal of this session is to teach you about static timing analysis. Right. So in the last lecture, we have seen many of the problems of the static timing analysis, but I feel that I should take one lecture, and that is the reason why I'm taking this lecture. Okay, and this will also help you in doing the assignments. But most importantly, the concepts should be extremely clear because timing is one of the very few topics which will be asked in every VLSI interview you give. Okay, and everywhere you go, the timing is the most important topic that will be asked for, right? If not the most important. Okay, so as of now, we have been discussing about the basic transistor, then the basic combinational circuit family, and then we have discussed about the layouts, then the power, and then the last topic which is remaining is the timing part. Okay, we have done some of the simulations, also not simulation, right? The questions earlier. Okay. Uh, we will what we will do, we will do the basics of the static timing analysis again, right? And I hope if you have any questions, anything on this, right, you feel free to ask at that moment itself. Okay, so before starting to the static timing analysis, what I will do, I will teach you the basic concepts of static timing analysis. I hope uh, all of many of these are actually been taught in the class. I hope you remember many of these things. If you don't know, it will be a revision for you, and if you have not seen, then you can ask questions on that. Okay, so the first is basic concept. Okay, so the very first thing which we have to understand that the majority of the designs in today's world are actually synchronous, right? Synchronous means that this actually works in one of the edges of the clock. Okay, so whenever the clock comes, the instructions will be executed, unless and until there is an explicit say that okay, the design is asynchronous, right? We assume that all the designs are synchronous. Okay, so let it be your the pipeline processor you have, right? Let it be your the GPU, the DPUs, and everything, right? Whatever you design, it will be working in the synchronous domain, right? You can take the example of traffic light controller. The counter goes on with a particular frequency, right? And that happens at the particular edge of clock. Okay, so what is the benefit of the synchronous design? They have various benefits. That's the reason synchronous designs are used everywhere. The first benefit is that it eliminates the race condition, right? So if you have a clock edge and when the clock edge comes, the all the operations happens, right? Until the next clock edge comes, anything new operation won't happen. That particular operation will be executed, right? And this particular thing will help you to eliminate race condition. Also, because of this synchronous nature, right, we can do pipelining, and all the processors which you have actually follows pipelining. Okay, and because of that, you can increase the throughput of your system. Okay, so that's the two important point, right? We assume in all the sequential design, whatever we have, all the sequential are actually edge triggered using D flip flops as a register, right? So whenever we talk about that, okay, we are using a flip flop, majorly we'll be talking about the D flip flop, and it will be edge triggered flip flop. Okay, now the most important thing is the D flip flop itself in the timing. Whenever we talk about timing, we talk about the timing between two different flops. Okay, you can see over here there is one flop. You can see over here there is another flop. Okay, so the timing is being calculated between the two flops, and because of that, there are actually two things, right? One is what we call as a launch flop, the other what we call as a latch flop. Okay, so launch flop means, right, the flop which is providing the data. Okay, there is some combinational circuit which is being actually been some combination logic is being performed, right? And then it will be latched into the next flop, right? And between this there will be a path. This is called as our timing path. Okay, so this is a very important concept, right? Whenever we talk about timing, we generally talk about the timing between two flops. The first flop will be called as launch flop. The second flop will be called as latch flop. Okay. Now, three important parameters when we talk about flop is TCQ, T setup, and T hold. Okay, TCQ means the clock to queue delay, right? It is essentially the propagation delay of this particular flip flop. Okay, the second thing is T setup. Okay, setup is the time, or the setup time is actually be defined as the time uh, data needs to be arrived before the clock age, right? So we will go into a greater detail about this concept. And T hold is uh, the time the data has to be stable after clock age. Okay, so let me get into detail of this timing parameter. The first timing parameter what we have is TCQ, right? That is T clock to Q. So this T clock to Q, right, is been defined as the delay between this clock, okay, and when the final output comes, right? So if you provide a clock, right, ideal expectation is that the output should come immediately, okay, but that actually doesn't happen. Okay, so if you provide the clock in this D flip flop, right, and you have provided the data, you see the data is already stable before the clock. Okay, so the final output actually comes after certain delay. Okay, this delay is the internal delay of the flip flop. Okay, and we call as this as clock to Q delay. Okay, this clock to this Q delay. Okay, that is the reason why it is called as TCQ. Okay, and again it can be of two type: TCQ low to high, right, where the clock the Q is going to low to high, right, and TCQ high to low, right, where the Q is going from high to low. Okay, so as soon as you provide the clock, the output doesn't come immediately. Output comes after some time, and this is called as T clock to Q. Okay, now the second thing is what we call a setup time. Okay, so setup time is the time the data has to arrive before the clock to ensure correct sampling. Okay, we will see the reason behind the setup time in coming slide, but to understand the setup time, using I have couple of examples. So if this is a clock, right, and this is the setup time, if you have, okay, the data has to change before that. Okay, change before that, it cannot change in this setup window. Okay, so this is a good part, good design. Okay, again if you see for this particular clock edge, the data is changing over here. Okay, so it is actually before the setup time, so this is also good. But if you see over here that the data is not changing, or actually changing in the setup window, right, we call this as a setup window. Okay, setup, it is a window, right, setup window. Okay, and it is changing in between, right, so the output whatever you will get will be incorrect. Okay, you don't know what output you will get, and the output you cannot say that it is correct, it will be incorrect. Okay, so this is how the setup time is defined. Is that clear to everybody? Okay, I believe so.
Yes, sir.
Okay. Now moving to the whole time. Okay, moving to the whole time, again after clock, so after this clock edge comes, the data should be stable, right, till this hold window. Okay, similarly, just like setup window, we have a hold window, so data should be stable after this. Okay, so this is an important thing. So that was the first design, and if I see the second one, right, again in this you see here the data is stable in the hold window, right, here also the data is stable in the hold window, right, but in this case you can see the after clock is come, this is the whole time, right, and data is not stable. Okay, data is not stable. Okay, data is changing. So if data changes between the whole window, then there is a problem, right, we call this as hold time violation. Okay, the previous was when it changes in the setup window, we call this as setup time violation. Okay, now the question is, okay, why there is a setup time? Okay, so why there in the flip flop we have to take care about the setup time? Can anybody tell me if anybody know the reason? Why there is a setup time requirement? Does anybody know? Not really. Okay, so does anybody know what design it is? Whatever I'm showing over here. Anyone? What design I'm showing over here? What is this design? Sorry.
Yet, let's transparent let's.
Transparent latch. Okay, now it's there are actually two latches. You can see, right?
Then it is flip flop.
Yeah, this is a flip flop. Which edge triggered? Can you tell me? Right. So this is a negative edge triggered flip flop. Okay, negative edge triggered flip flop. Okay, how does it will work? Okay, so initially if you see, the clock will be one. Okay, if the clock is one, whatever the d over here is, right? So d will be here. Okay, and this d will go over here, right? Here it will be d bar, right? And if clock is 1, right? So this will be 0, so this will be off, this will be on, right? It will be like that. Okay, so although d is over here, right? And if clock is 1, so this is also off, right? So whatever the output is, output whatever the earlier output was, right? So q was stable. Okay, now the clock is 1. Okay, as clock goes to 0, as clock goes to 0, right? What will happen? This will turn off. Okay, this will turn on, and d will be latched over here. Okay, so d will be latched over here, and this will also be turned on, so d will be passed from here. Okay, so d will be passed over here, right? Here you will get the d bar as an output, so whatever output you want to take, right? It will be q bar, right? Whatever the d you have passed, right? So and it will now wait for so if you again change this, right, it will wait for again negative edge clock, and when it will change. Okay, so this is how this particular flip flop will work, right? And please note that this is a negative edge triggered flip flop, right? You should know this particular circuit, because if you talk about the sequential design, this is the most important circuit. Okay, if you understand this circuit, you will understand everything. Just like what I have said in the combinational circuit, if you understand inverter, right, you virtually understand actually all the combinational circuit. Here, if you understand this D flip flop, you understand virtually everything in the sequential design. So the question is from where the setup window is coming from. Okay. So if you can see over here, when the clock was 1, okay, when the clock was 1, okay, the data, whatever you have, right, so this is on, right, because clock is 1, here it is 0, right, so this is on, okay, and you know that, right, this is a transmission gate, this is a transmission gate. Okay, so if suppose if you to want to write 0 over here, okay, and the output node is at 1, right, this is also at 1, right, so this is the previous data. Okay, now what you want to do, you want to write 0 over here. Okay, so 0 will go over here, right, then 0 will go over here. Oh no, it will be 1 actually, 0 bar. Okay, and if you see, 1 will come over here, then it will be 0. Okay, it will be 0. Okay, so I have actually made a mistake in the previous one. There won't be q bar, right? So that it will be actually q only, right? Because whatever data that will come over here, it will come here as a d bar, right? And when we'll go over here, it will be actually d only, right? So that's the reason we do not have to put any additional inverter. Okay, so if you come over here, it will be 0, but this transmission gate is off. Why? Because here it is 0, here it is 1, right? NMOS is off, PMOS is also off, right? So data is actually not latched, so you want that this connection to be completed. Okay, so when this connection will be completed, when the negative edge of the clock will come, right? As soon as the negative edge of the clock will come, this transmission gate will open, right? And this zero will be over here, right? So data will be latched and data will be transferred. Okay, so that's how the process works. Now the question is, right, for data to be latched properly, right, the for data to be, please understand, for data to be latched properly, this data, whatever zero was here, should be available over here, right, as the negative edge comes. If data is not available, right, at the negative edge over here, then there is a problem, right? So this entire time, from tg3 to t1 to t1 to 2g tg4, right, is actually the setup time, right? Because this is the internal structure of flip flop, which is saying that okay, the data should be stable, right, at least this much of time, for this much of time, such that data should not change before the latching. Okay.
Sir,
Yes.
sir, can you explain once more? I did not get.
You did not get it.
Yes.
So did you understood the flip flop part, right?
Yes, sir.
See, I'm assuming that initially my clock is one. Okay, initially my clock is one. Okay, here the data is one, the output is one. Okay, what I want to do, I want to write zero. Okay, so in this case, so if I yeah, if I make the clock one, right, and this is my line. Okay, so this is on. Okay, this is off, and this is on. Oh, sorry, this is also off. Okay, because the clock is 1 and this is 0, right? So this is on the clock bar. So here NMOS is connected to 0, it is connected to 1, so that's the reason it is off. And here also it is 1 and it is 0, that's the reason it is off. Okay, now what, when this 0 will be coming over here, right? 0 1 will be coming over here, right? And 0 will be coming over here, right? But for when we call the data is latched, it means that this closed loop is completed. Okay, then only you can call that the data is latched. Otherwise, if there is any change over here, right, this will change and this will change and this will change, right? So for data to be latched, what should happen, this transmission gate should be turned on. For this transmission gate should be turned on, the clock should go from 1 to 0. Okay, as the clock goes from 1 to 0, right, what will happen when the clock goes from 1 to 0, this will be turned off, right, this will be turned on, right? So whatever 0 was here and it was already a 0, right? So this the proper connection will be made. Okay, and you can see that the data it will be like this. Okay, it will be like this now, right? So whatever the data is here, right, that is actually properly latched. Okay, now the thing is, when this clock is coming, right, this data should be stable for this much of time. Okay, why I am saying that, let us take an example why I am saying that data should be stable till this much of time, right? So suppose clock is about to go 0, right? And suppose this actually takes some time. Okay, so the data was actually so let me make somewhere here. Okay, so the clock is about to go 0 like this. Okay, and data was actually 0. Okay, so this is my clock. Okay, data was 0, and suppose this time I am talking about, the setup time, right, is something like this. Okay, something like this. This much is the setup time. Okay, so what we are saying about the setup time is that the data should be stable like this. Okay, now what will happen, or data should be actually stable, right? It should not change. Okay, so if it is like this, it is like this, right? Or if it was earlier 1, right, and it is becoming 0, right, it can become 0 before this time, before this particular time. Okay, if it is not happening, if it is, suppose if it is happening over here, now what will happen? Okay, so you see that the clock is about to go to 0, right? And what happened, that earlier here, if suppose it was 1, right, if there is 1, then the data over here will also be 1. Okay, and the what happened, the clock has gone down, right? Clock has gone down, and before that the data has also gone down. Now what will happen as the clock goes down, right? As the clock goes down, it will actually see the data 0 coming from here, the data 0 coming from here. But this earlier what happened, we have passed 1 from here to here. Okay, here it is still 1 because this 0 will take some time to propagate, right? This is the setup time. Okay, so as soon as this goes down, and if there is 0 and earlier the data was 1, right, which was here, and this 0 has not made this 1 because of the delay, right? As soon as you make this go down, right, there is a conflict between 0 and 1, right? Now you don't know what data to be latched, right? So that's the reason up to this much of time, the data should not change. Did you get the point?
Yes, sir.
So that's what we call as setup time. Okay, T setup equal to, and what is the time? It will be TG3, T1, TI1, TI2, and TG4. Okay, so that's where the setup times actually come into picture. Okay, now if you understand setup time now, I will just go to the hold time. Okay, so what is the hold time? Is suppose the data is actually latched. Okay, so data is latched, suppose here as 0. Okay, so you have done everything, and this 0 has to be transferred, right, from here, right? So before transferring the data to this particular part, the data again should not change. Okay, so data should not change. Okay, so from there the whole time actually comes into picture, right? And if you see over here, in one flip flop, right, if we are just talking about only one flip flop, I have written that the whole time is negative of tg3 and ti1, right? Negative of tg3 and ti1, right? And here I am writing it negative whole time, right? And the reason behind that, that in single flip flop, if you see, right, there cannot be an whole time violation. Why? Because as soon as this clock edge goes low, right, this turns off, right? If this is turned off, right, the data won't change after the clock edge goes low. Okay, so in that manner the whole time violation won't occur, right? Whole time violation will occur if, see, the clock edge over here has gone low but it is still open. Okay, and this can happen, this kind of things can happen. Why? Because if you see there are clock and, if you see there are clock and clock bar, right? And how the clock and clock bar will be generated? So if there is a clock, right, you will put an inverter and you will say the clock bar, right? So if you see that the clock and clock bar will not be generated at the same time, right? If clock goes down, right, from 1 to 0, the clock bar will go from 0 to 1, but after some time, right? And this time will be the inverter delay. Okay, so you have to take care that, okay, although I have made this down, right, here it has to go up, right? If you have made this down, here it has to go up, right? And till it is going up, right, this much of time the data should be stable. Okay, so in that manner, the whole time violation can be avoided, right? So if you provide that particular time, right, and if both of them actually turns on and off at the same time, then there cannot be whole time violation, right? Actually, you have more buffer time, right? You actually have negative hold time. Negative hold time doesn't mean anything as such, right? But maybe to understand, we write this kind of thing. Hold time is actually 0 in this case. Okay. Okay, so coming back to this now, once we understand the setup and hold time, what we have to do is we have to define two problems that is actually occurs in the synchronous design. The first one is what we call as max delay. Max delay means the data does not have enough time to pass from one register to the next before the next clock edge. Okay, so if I make a register, right, if I make a flop, this is how the flop, sorry, this is how the flop will look like. Okay, and there is D, this is Q, and there is D, and this is Q. Okay, and there will be some combinational logic, right? What do you want? That if I give a positive edge of clock over here, right, and it is going down and it is becoming like that. As soon as you give positive edge, this data will pass from here. It will pass Q from here. It will do something, and the data should be available when for this, right, in the first clock edge obviously it won't be available, but in the second clock edge, right, the data whatever you have passed from here, all the computation should be done before that, right? So whatever the delay this path is taking, that is called as the max delay constraint, right? So that much time period you have to provide. Okay, so this time period, right, from the first clock edge to the next clock edge should be at least this particular delay, okay. Now the second thing is the min delay. It means that what happens that there is a flop, okay, and what you have done is you have provided the clock, right, at the same time, okay, and see this flop will have some setup and hold time, okay. Now what happened that this Q and this is D, this is Q, this is D, right? This path was so fast, right, very fast, okay. It was so fast that data has reached in the whole window itself. Okay, if data changes inside the hold window, then there is a problem, right? So the hold violation can happen, right? So in the first case, what is happening, the data is not reaching, so that's the max delay constraint. In the second case, what is happening, that data is reaching earlier than expected. Okay, so it was too fast. Okay, so the whole time violation will be there. Now can you tell me if there is any circuit where the whole violation can occur, where the this particular flop to flop path is extremely fast? Anybody tell me an example of any circuit where there is no combinational circuit between multiple flops, it is directly connected? Any digital circuit, you know? Anyone?
Counter circuit or
Counters,
register?
right? So counters, registers, right? Shift register. So if you do a VLSI, or if you have say a synthesizer tool, right? And when you are designing counter, right, you should be extremely careful when you design counters and shift register. Okay, because and the later on there can be hold violation in that. Okay, so yeah, so the example where the hold violation can occur, right, are the counters and registers where there is no combinational delay between the two flops. Okay, so I have discussed, right. So if there is a max delay violation, we call that as a setup path, right? And if there is a setup violation, suppose there is a setup violation, what happened that okay, there was two flops, okay, and there was something, right, and some combinational logic, and I have provided a clock of say 5 nanosecond, okay, and there is a setup violation. Can anybody tell me how do I remove this setup violation? That okay, the whatever the data is there, it is not reaching in the given time period. What should you do? Anyone? Just a guess. It's very simple, right? If there is a time period, I've given you 5 nanosecond time. Okay, this is the time you have for
We
this.
can decrease the size.
You can decrease the size. Okay, that's an interesting answer. Decrease the size of logic.
Um, Path.
Decrease the size of path. Okay, that's true, right? So what you can do, you can make the path faster, right, by making the path LVT, HVT. So LVT, I think in the last we have seen that, right? In the last class, what we have seen that okay, what you can do, you can decrease the path, right? And by decreasing the path, you can do yeah, you can do this. Decreasing by decreasing the path delay, you can do this. Now, do you have any other solution, right? If you don't want to change the path, suppose path is fixed, right? The hardware is fixed. What you can do? You have made a chip out of it. Okay, you have made a chip. You have fabricated a chip, right? Now, what you can do if there is a setup violation? What is the easiest way?
Changing the clock.
So what you do? You change the clock to 5 from 6 nanosecond. Right? Give more time, reduce the frequency. Right? So in that manner, what will happen that there won't be any setup time violation, right? So setup time violation can always be fixed, right? So it's not a very big issue. Okay. So by just changing the clock period, you can change. But one of the very famous interview question, right, which I am going to ask, okay, and you should tell me immediately the answer, right? I have two flops. Okay, these are two flops, right? I'm repeating the question. These are two D flip flops. Okay, this is D, this is Q, this is D, this is Q. Okay, and this is the path between this, some combinational path, right? And there is a hold violation over here, right? What do you mean by hold violation? That, okay, if there is a clock, okay, which is coming at the same time in both, right? So data path was so fast that the data has changed within the, okay, so data should be stable, but data has changed within the whole window. Data was very fast, data path was very fast. Okay, now you tell me, how do I remove the hold violation? Okay, you are allowed to make the changes in the circuit. That's the first question.
Introducing delay.
Introducing delay. How do you introduce the delay? That's an excellent answer.
Register can a buffer or a register can make a delay there in the circuit.
Okay. We cannot include register, right? Please note that registers are flops. Okay, but we can
Okay,
use buffers. Okay, so
and then it will be a buffer.
yeah, what you do is you should include the buffer, right? So if the path is very fast, you add multiple buffers. Okay, so this is like that. Inverter chain you can add, okay, such that it won't change the functionality as such, but it will provide you the delay. Okay, so this was not a famous interview question. The famous interview question is, okay, you have made a chip out of it. Okay, so what you have done, you have fabricated everything and you have made the chip, right? Now the question is, now you found out that, okay, there is hold violation, right? How do you remove it after fabricating it? You cannot change the hardware anything. Can anybody tell me? Right. So if you detected in the software level, it is good, right? You add the buffer and you change it. But what if my chip has the hold violation? Yes.
We will increase the paths
We will increase the paths. Can you elaborate on that? Yeah.
by combining two chips.
By combining two chips, right? So you cannot do that, right? Because see, inside a chip, there are paths where the hold violation is occurring. Okay, so if you combine multiple chip, it won't actually change anything. Anybody else has answer?
By
Is there anything we can do with power?
No, we cannot do anything with power. Okay, so let me tell you the answer, right? So actually, there are no answers. Okay, so if there is hold violation after chip is being fabricated, you throw the chip. Okay, the answer is you throw away the chip. You cannot do anything. right? Because hold violation can only be removed if you introduce the delay, right? And after the chip is been fabricated, you cannot introduce the delay between the two logics. You cannot do that. Okay, so hold violation is independent of the clock frequency. It doesn't matter what frequency you're running and anything like that, right? If there is hold violation, right, after the chip is been fabricated, you throw the chip. Okay, that's the reason whenever you design the chip, right, and whenever you go through the entire fabrication flow, you have to explicitly be careful about the hold violation. There should not be any hold violation, right? I have shown you that if you have setup violation, right, you can just reduce the time period, sorry, clock frequency, and increase the time period. It will actually remove the setup violation, right? So eventually, if your chip will work, right, you do not have to worry. It will work slow, but your chip will work. But if you have hold violation, that your chip is not usable. Okay, so yeah, that's the argument. I hope that is clear to everybody.
Yes, sir.
Right. So now what we will do is we will derive the timing equation for the setup time. Okay, so if you see that these are my clock two paths. Okay, this we have already done. Okay, I will, sorry, I'm going fast, right? So if you see, okay, just ignore this particular part, right? If you see that what time I should give, so the time I should give, the time period should be decided between the delay of this. Okay, so the delay between the two flops, okay, in an ideal condition. So what is the delay in the ideal condition? The first delay which will come is t clock to q. Okay, this is t clock to q. Okay, that's the reason t clock to q is the first delay. Then the second delay is the combinational logic itself. Okay, so t com. Okay, and the third thing is it should have at least how much time, that is the setup time of this particular flip flop. Okay, that is tsu, right? So please understand, right, whenever we are defining this equation, right, whenever I'm talking about the setup time, I'm actually talking about the setup time of the second flip flop, not the first one. Okay, for the first flip flop, what I'm taking t clock to q, right? There is the delay of the combinational circuit, and for the second flip flop, I am taking the setup time, right? This concept should be absolutely clear to you. Okay, and the timing should be greater than t cq plus t logic plus t setup. Is that clear?
Sir, why to take like that?
Why do you take like that?
Yes, sir.
See, the data will be passed. So as the clock comes, right, the data will be passed from here. This Q will be transferred, right? So from clock to Q will be transferred, right? And who will latch the data? The data will be latched by this particular flip flop. Okay, that is the reason the latching flip flop setup time has to be taken care. Okay, if you see that, okay, when the next clockage is coming, right, so suppose I have this clockage, right, so data has gone from here, right, and this goes like that, and there is the next clockage which is coming, right, and this data, right, actually changes in the setup window, in the setup window, right, of which flip flop, of this flip flop. Okay, then there will be setup violation, right? So data is coming to this flip flop, then that is the reason why we are taking the setup of this particular. Okay, and for this flip flop, data is going from here, right? But when we see, if I have another flip flop over here and I'm calculating the timing path, then I will see the setup of this flip flop. Okay,
Yes, sir.
now we can have non-idealities in our design. Okay, so is first is if I have the delay in the clock path. Okay, this is my, what we call this as delta skew. Okay, skew, some positive delay is there. Okay, so what happened that, okay, I have a clock which is coming like this, right? This is clock 1. Okay, then I have another clock which is delayed actually. Okay, so it is like this, right? So what I am saying, that this is the flip flop which will actually latch the data, right? So as soon as this clock comes, right, this clock comes, the data will be transferred from here. So as soon as this clock comes, the data will be transferred from here, right? And I'll be waiting for this particular clock, okay, to latch the data. So how much time do I have? I have actually now increased time available for me. Okay, so the total time which was earlier t only, right? Because of this q, this has actually given me positive uh, time period added to my this particular design, right? So that's the reason the total time period will not be now t, it will be t plus delta sq. Okay, and similarly, if there is a margin over here, it means there can be the time period can be increased by certain amount. This particular delay can be increased to the certain amount. This delay has to be added to the total delay. Okay, so this is the extra margin we are taking. Okay, so that's the reason it is adding over here, right? So this is very simple because it is in the path itself, right? But this you should understand that if I have a skew, right, and it is a positive skew, right, if your clock going from here to here, right, what will happen that you see that the first clock is coming to this flip-flop at this time, but the clock 2, the second clock is actually coming delayed, right, as compared to this one, right? So I am actually latching the data over here, so I have increased time period. How much increased time period? T plus delta sq. Okay, and this equation is a very important equation to you, right? Simplified manner, you should use this equation in your all exams and all, right? And if you include the non-idealities and all, right, you use this particular equation. Okay, this is for the setup and max time constraint. Okay, so now moving to the next part, where is hold or the minimum time constraint, right? So if you see over here what I have said in the minimum time, right, that your data path is so fast, your data path is so fast that the data is changing in the whole time itself. Okay, so when you, and one thing you need to understand, and these are see the very important things I am talking here, that whenever you check the setup time, you're checking at the second clock edge of this flip flop. Okay, you see that, okay, this clock are coming after some time, right? But you're not checking the setup time here, you're checking the setup time here, right? Because you're providing the entire time such that the data path passes, right? And you are checking the setup time over here. Okay, so whenever we talk about second setup time or the max time constraint, you're talking about the second clock cycle of the second flip flop, not the first clock cycle. Okay, but when we talk about the whole time, it is the first clock cycle of the second flip flop. Why? Because you see, suppose I have a clock over here, right, which is my clock 1, right, and I have a clock over here which is my clock 2, right? Right, suppose abhi now we are taking the ideal condition. Okay, what happens that as soon as this clock comes, okay, I have a data. Okay, data is suppose input is 1, right? Initially it was 1 and now I have made it 0, right? What happens that, okay, this was 1, right, and then so the it was 1, then it has been made 0. Okay, and this is so fast that it has made 0 here itself. Okay, in the hold window itself. Okay, if that happens, then there is a hold time violation, right? So whenever you are calculating hold time or we are checking for the hold time violation, you are actually looking into the first clock edge of the second flip flop itself, right? Because as soon as this clock comes, right, data has moved zoop very fast to this particular flip flop, and the next flip flop actually requires some time to be data to be hold, right? And but data has changed in between, right? It means that whatever the delay of this path is, right? What is the delay? Delay is t clock to q, right? Plus t combinational logic, right? That should be greater than the whole time, right? Whatever the time it is, right? So data should be greater than this delay should be greater than that, such that it changes after that, right? So then there won't be any problem. Okay, so from here the whole time constraint is coming, and one of the important thing to note here is that the whole time is is independent of time period. You see, there is no time period in the whole time equation, right? If you see the setup time, there was time period, but hold time is independent of the time period, right? That's the reason if there is a failure in the whole time after making the chip, right, you cannot do anything, right? You only have the flexibility of changing the time period, and that too is not in the whole time. Okay, so now if I add nonlinearity over here again, the skew will be added to the whole time. But this margin, now we are taking the best case time, right? Here we are taking the worst case, right? So that's the reason we have added to the path. Okay, but here what we are taking is the best case, right? It is very fast, right? And we have a negative margin, so we have subtracted from the path. That's how it is. Okay, so this is the equation for the whole time. Any questions? Wonderful. If that is there are no questions, then this is just a summary, okay, of whatever I have said, right? So this is the equation for the setup time. This is the equation for the whole time. Please note that these slides are available whenever you go to the YouTube link, right? I have provided a link for these slides, right? And whenever you are actually preparing for any VLSI interview, you go through this slide, right? There are multiple slides available or YouTube tutorials available on timing. You may want to go through that also, right? But you should actually go through this. Okay, so you should take care about the timing concepts in the VLSI. Now, once we understand the basic timing, where what we have done, we have understood setup, we have understood hold, right? Where we have understood TCQ, T clock to Q, T logic, okay, then T setup, okay, and also T skew, right? Multiple things we have seen, okay. We have seen all of this thing, and we have also seen the setup and hold time origin also. Okay, now what we will see is what we call as static timing analysis itself. Okay, so if something is called static timing analysis, it means there should be a dynamic timing analysis also. Okay, so how static timing analysis and the dynamic timing analysis is different. So whatever analysis we do in the cadence, in the spice level, where we do the simulation, we check all the functionalities are correct or not, right? That is called as dynamic timing analysis, right? You do the simulation. If you have used Vivado, if you use model sim and all, right? Whatever the simulation you do, that's the dynamic timing analysis. You see, right, if there is a timing violations or not, or everything like that. Okay, where the static timing analysis doesn't take inputs and do the analysis, right? Whenever you want to do a dynamic timing analysis, whatever analysis you do is a dynamic timing analysis. You have to provide inputs to your design and you check the output, right, if everything is coming correct or not. But in the static timing analysis, the beauty is, right, you do not provide any input. Okay, you do not provide any input. So that's the first point. It is actually exhaustive and very fast as compared to the dynamic timing analysis. I don't know if you guys have used cadence or spice level simulation. If you want to do very large design spice level simulation, it takes very large time, right? So that's the reason this entire static timing analysis concept has come into picture. Okay, the only or the main disadvantage is, right, so the proper circuit functionality is not checked. Why? Because you have not provided input, you are checking output, right? So that's the reason the circuit functionality is being not being checked. And if there are some exceptions, okay, you have to explicitly take care. We will see what kind of exception I am talking about. Okay, so, what is the limitations of static timing analysis? It is only useful only for synchronous design. If there is a design which is clocked, then it is useful. There can be feedback loops in your circuit design, right, which can be asynchronous. And static timing analysis cannot analyze this combinational loop or asynchronous issues. Now, there is one term that is called as clock domain crossing, right? So what do you mean by clock domain crossing? And it's a very famous interview question. Is that, okay, I have a system or a chip which is working at say 5 gigahertz, right? Very optimistic I am over here. And there is another chip which is working at say 2 gigahertz. Okay, now if there is a communication between these two chips, right? These are two clock domains. One is at 5 gigahertz, the other is at 2 gigahertz, right? And if the both the positive edge of both the this particular system are not synchronized while doing the data transfer, then there can be a problem. What is the problem? The data can be lost, right? Because the timing are not actually synchronized, right? For handling such kind of problems, right? And this is actually called as clock domain crossing, right? Clock is actually crossing two different domain. Okay. And for handling such kind of issue, you do not have or static timing analysis cannot help you. We have different tools which can do this clock domain crossing analysis. Okay. So and also it does not check the glitches and all in the pins if it comes. Okay. So when we talk about static timing analysis or the timing, we talk about timing paths. Okay, because there should be a start point and there should be an end point. Okay, the start point can be from clock pin of the flip flop or the input ports, and the end point can be input pin of the flip flop or the output ports or the memories. Okay, so I will actually show you, right? There are actually four timing paths. You have to understand very carefully. Then the one which we have seen is this one. Okay, so this is from D flip flop to D flip flop, you can see, right? Output of this flip flop to input of this flip flop. Okay, this is the timing path. There can be another timing path where the output, the register output and the combinational delay, and it is not connected anywhere in the next flip-flop. Okay, so which is called as register to output. Then there can be another timing path which is input to register. Okay, and there can be only input to output for the combinational design, right? If your design is fully combinational, you do not have flops, right? There can be four kind of timing path. When you do the static timing analysis, right, you have to actually take care of all the timing paths. Right? Any question in the timing paths? Okay, no questions in the timing path. So apart from the four different type of timing path, we have also three different other categories of timing path. One is clock path. Okay, so clock path is a path where the clock is being transferred. You see, this is the clock, right? And clocks are generated by PLLs, okay, phase locked loop. There is a circuit which actually generates the clock, right? From there, it is going to the flip flop, okay, and there can be buffers in the path such that the clock is being driven to the final output, right? This path is called as clock path, right? This is the clock is going from the source generation to the input of the any of the flip flop. This path, if you will traverse, this path is the clock path. There can be another path which is called as clock gating path. Okay, clock gating path means if you see there is a clock, right, and it is there can be another signal over here. Okay, another signal which is called as say gating signal. See, if this gating signal is zero, the output will always be zero. Okay, if this gating signal is so see, if this is my gate signal, gate, right? If this is zero, right, the output is zero. Okay, if this is one, right, whatever the output this will come, so clock here it will come, the output will be clock, right? So what you can do, you can selectively turn off the clock. And why do you do clock gating? Anybody knows? Anybody knows what is the reason of doing this kind of clock gating in the circuit? Anyone? Okay, so the main reason behind doing the clock gating is to save power. I have multiple times discussed with you that the major source of power consumption is the dynamic power. When does the dynamic power consumption occurs? Whenever there is a change in the inputs or output, right? When the input and output will change, right? At the clock edge. So the higher the if the clock is running, it will still consume the power, right? So you turn off the clock. If you don't want that circuit to be what? To be stagnant. Okay. The third path, which is here, is an asynchronous path. Okay, so suppose reset is signal which is going on, right, with some logic is there, and it is just resetting it. Okay, so there are three kinds of path which we have, which we do for the timing analysis: clock path, clock getting path, and asynchronous path. Okay, previous to that, four categories of timing paths were the R2R, right, R2O, I2R, and I2O. Okay, so now once we have understood this, right, we have to understand that, okay, how does this static timing analysis works? Okay, so for doing the static timing analysis, what you do is you actually find out all the possible paths which are available, all the paths, right, and then find the delay of all the paths, right. Whatever the maximum delay you get, right, that delay will be what what it will be. It will be the worst case delay, and that will define the timing. Okay, and how do you calculate the delay? Delay will be cell delay, the delay of the gate, or the net delay, the delay of the wire itself, right. So both the delays will be added and the final total delay will be calculated. Okay, so you can so whenever you do the timing analysis, right, you will generate, or the tool will generate for you, so say 1,000 of paths, and whatever the path has the highest delay, it will actually pick that. Okay, so that's how the STA works, right. And in the STA, what you will do, you will actually check for both setup and hold constraint. Okay, so whenever you are doing this timing analysis, you have to check for this setup and hold constraint, which I have already discussed, right. And one of the important terms in the timing is what we call as arrival time, required time, and the slack, right. The important term is the arrival time, and the time represents at which the data arrives at the input of the receiving signal, the receiving sequential element, right. So if this is the receiving sequential element, right, so what is the time after which the data is arriving? Okay, so that is called as arrival time. If you see, it is D1, so clock to Q, plus D2. Okay, so the logic delay, and it should actually be the setup also here, TSU, right, and plus but you can see over here that this D4 has been subtracted from here, so I will remove this, that I will add over here D4. Okay, so T clock to Q plus T logic plus T setup. Okay, now the required time is the time which you have given. Okay, the time period which you have been given, right, so this will be the time period, so the T, right, plus if there is any skew, that D3. Okay, and the slack is the difference between the arrival time and the required time. Okay, so this will be, the slack will be actually D1 plus D2 plus D4, not like that. So required time minus arrival time, because required time is whatever the clock frequency you have given. So the slack is equal to, okay, so T plus D3 minus D1 plus D2 plus D4. Okay, so this is what slack is. And uh, the thing is, the slack should be 0 or positive. Okay, so if slack 0 means whatever the time that was required, you have provided the exact same time, right. If slack is 0 or greater than 0, it means that you have provided enough time, more than the time that is given, right. If the slack is negative, it means there is a setup violation. Okay, so these terms you should be very clear about.
Okay. Yes, I want to know one thing, that from Slack, is it possible to calculate the speed of operation or something else? That is speed of operation. That
Yeah,
is,
so
it.
if the slack is 0, means whatever the time period you have defined, right, that is the maximum frequency that you are working on,
Okay,
right.
and if Slack is positive,
Positive
then
means that you can reduce the time period. By how much? By
okay,
that particular slack.
okay. The but the operations speed of operation is 1/t. That is the clock I have given there.
Exactly. So let me just write down. So speed frequency will be 1 by uh, t clock. So see, 1 by total time I will write. Okay, 1 by t. Right. So in this particular case, it will be 1 by t plus d3 minus slack. right? If slack is 0, so that is the maximum frequency you have. If slack is positive, the frequency can be increased by that much. If slack is negative, right, the frequency will be reduced by that much. Is that clear? Uh, is that clear?
Yes, yes, yes.
Okay. Now, the final part of this lecture is two of the things. This I have put intentionally that you should know, right? Because many of the students I have worked with, right, they have said that okay, these kind of questions are asked in the interviews, right? So I have just included this, and yeah, these are important concepts. What we call as timing exceptions. Okay, so there are two timing exceptions. The first is a false path. The second is a multi-cycle path. Okay, so whenever you do the timing analysis, right, you have to take care about this timing exception, and I will just show you, right, what do you mean by timing exception, right? So this is the timing exception for the false path, right? False path means that okay, there is a path which is actually being shown from one input to another output, but that path will not be practically possible. Okay, and how and please let me know, right, if you don't understand this concept, right, and how does that will work. So suppose if this is provided as 0, right, so this will also be 0 because the cell is 0, right? In that case, this input will be selected and this input will be selected. Okay, so the path will become from here to here, right? This particular path, right, from here to here will never arise. If you see that, it will never arise. Why? Because if you make this to 1, right, this will also become 1, right, and the path will be from this to this, right? So the red one which I have shown, that this one will never happen. Also, this one will also never happen, right? So these are called as false path, right? Because you've designed the circuit like that. There are actually no way by which the data can traverse through this path or this particular path, right? These are called as false paths, right? I've given intentionally taken this example, right? And if you do the timing analysis, right, you are actually considering all the paths. You should not consider this false path. Why? Because you see, when you do the timing analysis, you have to actually figure out the fastest and the slowest path, right? And when you do the analysis, right, you see this is one of the false path which is making, and this is a slow logic, and this is the slow logic. Obviously you will make if you are not including or taking care of the false path, you will assume that okay, this is the slowest path, right, and I will make t about this, right? But this was actually not the slowest path, because this path will never occur. The path will occur like this, right? And you could have improved the time period by some time. Similarly, when you are doing the whole time check, right, you will see that okay, this is the fastest path, right? And if there are violations, that okay, we will see that okay, there is some whole time violation, but this path will never occur, right? This, the path will be from here to here, right, or the path will be from here to here. So there will be case that the whole violation is not occurring, but because of these false paths are there, right? If your tools are not smart enough, right, and if you have not explicitly specified this false path, then your tool will not give you the optimized result. Is that clear, everybody? Is that clear?
Yes, yes.
Right, so this is what we call as false path. I have another exception where we what we do, we define multi-cycle path, right? So suppose if I am working at 1 GHz frequency, right, which means time is 1 nanosecond. Okay, so but this logic takes 3 nanosecond. It is somewhere in the design, right? The easiest way to take care is you reduce the clock frequency by 1/3, that is 333 megahertz, right, and run the entire system in 333 megahertz, and the problem will be solved, right? But the problem is that you have designed such a huge logic, right? And there is one small part which is actually taking 3 nanosecond of time, and because of that, you are actually reducing the clock frequency of the entire design, right? Is that justified? This is not, right? So what people do, what they do is they make sure that okay, this kind of logic which is actually taking multiple cycle large time, you actually run at 1 gigahertz, but you provide actually 3 clock cycle to this, okay, such that the source clock is actually changing at 3 gigahertz, sorry, 1 gigahertz, but the capture clock will actually run at 333 megahertz, right? Although the input is changing, right, the final output won't change. Okay, so this will only be happen when the clock has been taken care. Okay, the final logic has been passed after 3 clock cycle, right? But if you do the analysis using static timing analysis, again it will consider that I have a very large path, and you decide the timing according to that. But you should have explicitly make sure that whatever tool you are using for designing this, okay, please take care that okay, this is a multi-cycle path, you define that, and don't decide the frequency on the basis of that. Okay, decide the frequency basis of the rest of the circuit. Okay, let me see if I have some slide. Okay, no. Right. So that's all for today. Okay. So I have what I have done is I have not discussed any question today because the questions have been discussed in the last class itself. Right. But what I wanted to tell you about the basics of the static timing analysis and the timing concepts. Right. I just wanted to revise for you because it has already been discussed in the class, many of the concepts. Right. And whatever concepts I have discussed are actually the concepts which are majorly been asked in the interview. Why it is asked in the interview? Because these are important concepts, right? As a circuit designer, these concepts should be extremely clear for you. Okay. So I teach all these slides. So the slides are my slides from my Gandhi. Okay. So I teach that in my design course. I thought that okay, I should teach this over here also because this was one of the topics in the VLSI design part. I hope you have understood. If you have any question, feel free to ask.
Okay, I have one question from this slide, a
Yes.
multi-cycle path that you have told as the say combinational logic in this the logic whatever it took 3 clock cycles. So, but in meantime, when it process for the 3 clock cycle, if there is any input appears at the source, then what happens?
I got your point, right? So this is actually not showing the complete picture. So what we actually generally do, so we have this SCLK, okay, and we have an AND gate, okay, and we have the clock. Similarly, here also we have this DCLK, right? DCLK, right? And not DCLK, and AND gate and the clock, okay. Now these two signals, okay, these two signals, this particular signal which I am talking about, it actually changes after 3 clock cycle, right? It becomes 1 after 3 clock cycle. So what it will do, it will make sure that this clock is coming to, this is anyway coming after 3 clock cycle, but although this clock is changing, right, till 3 clock cycle it won't pass any clock. If this don't pass any clocks, the data, although it is changed, but it won't pass through this particular path. Is that clear?
Yes, yes.
Okay.
Actually, my outer world clock have the same frequency, 1 gigahertz,
Yes.
but the speed of operation is reduced by one third. That is, for my circuit, the speed of operation is 333 megahertz right
Exactly.
now. 333. Okay, okay, understood.
Okay, then. Thank you everyone for joining this session. I will have the last session in the next week, and so that will be the questions will be on the week 12, and then after that I will have a summary session and maybe some of the tips and tricks for the VLSI interview, how to crack it. Okay, in the last session, and hopefully we will end the course at the high note. So thank you everyone for joining. Let's meet
Thank
at
you.
next time. Okay.
Okay, thank you. Thank you.
Thank you.
Sir,
Yes.
Uh, can you send me the link for the YouTube so that I can check the previous classes also?
Yes, 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 definitely. Just 1 minute. So, welcome everyone to live session 9. So, I'm sharing in the chat, right? So, this is the playlist. I will upload this video also soon by today itself.
Okay, sir. And sir, there is also a doubt in a previous question of that you arise.
Okay.
Sir, you told that if there is a hole setup in the chip,
Yes.
in fabricated chip,
Yes.
then we should dispose of it.
Exactly.
Uh, Actually, sir, I think there are many types of fabricated chips that can have such type of errors. So, is there not any other thing that we can do without disposing of?
Not really, actually. So, the thing is, um, so see, the thing is, we now our the design process has become so advanced that this time of hold violation doesn't come, right? We the tools we have, right? We take additional margins such that the hold violation doesn't happen, right? So we have actually recently here at IIT Gandhinagar, I have led the team, right? So which has we have done two tapeouts, okay? So in that we have explicitly make sure that this kind of violation doesn't happen. Okay, but once if we did the design for something by some means, if there is a hold violation, you cannot do anything, so that particular uh, chip will be of no use for you.
Okay, sir.
Any more questions?
No, sir.
Okay, then thank you for joining. Okay, we'll meet next week.